Imagine losing an arm and then regaining movement just by thinking about it. That's the promise of brain controlled prosthetics, where engineering meets neuroscience. These systems, they read tiny electrical signals from muscles or nerves and convert them into motion through robotic actuators. The technology that sits at the intersection of control systems, sensors, and rehabilitation medicine. Engineers work closely with clinicians to ensure these devices are intuitive, reliable, and safe for daily use. In this presentation, we'll explore how the technology works from electromyography and targeted muscle reinnervation to signal processing, control algorithms, and hardware design. We'll also look at how the NHS and other healthcare systems are adopting to these devices, making advanced prosthetics more accessible. By the end, you'll understand not just the mechanics, but the human element, how thoughtful engineering can return independence and dexterity to users. Every prosthetic arm begins with signal acquisition, the process of capturing bioelectric data from the user. These signals, often in microvolts, are then amplified and cleaned up using analog filters before being processed digitally. Engineers use DSP, digital signal processing, to extract patterns that correspond to specific muscle actions. From there, control algorithms translate those patterns into smooth, proportional movement of motors and actuators. Think of it as designing a feedback system that interprets intent in milliseconds. Each subsystem must minimize latency, avoid noise, and ensure stability under varying loads. Biomedical engineers also collaborate with material scientists to balance mechanical durability with user comfort. This combination of precise electronics and ergonomic design makes the system feel almost natural, allowing users to perform everyday tasks like gripping a cup or typing. TMR is a surgical innovation that changes how engineers design prosthetic control systems. When an amputee undergoes TMR, the residual nerve that once controlled the lost limb are rerouted to new muscle sites. These reinnervated muscles act as biological amplifiers, producing strong EMG signals that engineers can detect easily. Each muscle becomes a channel for a specific motion: hand open, close, rotate, and so on. For the prosthetic control unit, this means high resolution input data and a more intuitive user experience. From a systems engineering perspective, TMR improves signal reliability and separation, making pattern recognition algorithms more accurate. It also reduces the cognitive effort required from the user. Instead of learning abstract commands, they simply think about moving their hand. This surgical electronic partnership exemplifies how medicine and engineering converge to recreate natural movement. Electromyography is the interface between biology and electronics. EMG sensors detect the electrical potentials that occur when muscles contract. These signals are tiny, often less than a few microvolts, and can easily be masked by noise from nearby electronics or motion. Engineers use high input impedance amplifiers and bandpass filters to isolate the desired frequency range between 10 and 500 Hz. Once clean, the signal is digitized for processing. Electrode design plays a big role. Dry electrodes are convenient but sensitive to skin impedance, while wet or gel electrodes offer better conductivity. Some systems even use implantable EMG arrays for long-term stability. Precision here is critical. If the capture process introduces delay or distortion, the whole control loop suffers. The challenge is creating a sensor network that feels invisible yet captures the body's electrical language faithfully. After the EMG signal is captured, it moves through a carefully engineered processing pipeline. The analog filters remove low frequency drift and high frequency noise, producing a stable waveform. The signal is then rectified, converted to absolute values, and smoothed to find the envelope that represents muscle effort. Next comes feature extraction. Engineers compute metrics like root mean square, mean absolute value, and frequency components using fast Fourier transform. These features become input for classification algorithms such as support vector machines or neural networks. The classifier decides whether the user intends to open, close, or rotate the hand. Finally, a control module translates that decision into a motor command. Each stage is optimized for speed, accuracy, and adaptability. Together, they transform biological chaos into smooth mechanical action. Control algorithms are where software meets biomechanics. A proportional control system adjusts grip force based on how hard a user flexes their muscles. Similar to how natural muscle tension works, engineers design the systems to translate electrical effort into motor torque seamlessly. More advanced algorithms include adaptive learning, where the system refines its response based on real-world data from the user. Safety layers constantly monitor for irregular signals to prevent hardware strain or unsafe motion. Motion mapping, meanwhile, defines how each signal corresponds to a specific movement or grip type, from pinch to power grip. Engineers must tune these mappings to feel intuitive. It's like calibrating an instrument that plays in harmony with the user's intent. Behind every prosthetic hand is an embedded hardware system that handles computation and control. The microcontroller receives processed EMG data and drives miniature motors via motor driver circuits. Force sensors provide feedback to prevent crushing delicate objects, while encoders track finger position. Engineers also integrate Bluetooth for firmware updates and telemetry. Power management is another crucial aspect. Lithium polymer batteries must deliver consistent current while remaining lightweight and safe. The socket, the physical interface with the user, is designed using 3D scanning for comfort and alignment. The challenge lies in balancing performance with portability, maximizing computation and torque without adding bulk. Hardware teams often iterate through thermal modeling, vibration testing, and user trials to fine-tune the design. A prosthetic arm doesn't exist in isolation. It's part of a healthcare ecosystem. Engineers work with clinical teams to integrate devices into hospital workflows. 3D scanning ensures precise fit, reducing pressure points, and improving signal quality. Rehabilitation software allows therapists to monitor progress and adjust training programs. Many systems include clinician interfaces for updating firmware, calibrating sensors, and logging usage data. Cloud analytics take this further by tracking long-term performance trends, battery health, and even EMG signal drift. These integrations make maintenance predictive rather than reactive. For engineers, interoperability is key, ensuring that data moves securely and seamlessly between prosthetic patient and healthcare provider. This fusion of engineering and clinical feedback creates a smarter, safer rehabilitation loop. Every medical device must meet strict standards, and prosthetics are no exception. Engineers perform IEC 60601 tests to verify electrical safety, ensuring isolation, leakage current limits, and protection against shock. EMC testing confirms that nearby devices like defibrillators or monitors won't interfere with control signals. Mechanical reliability is equally important. Actuators are cycled thousands of times to test endurance. Latency is measured in milliseconds, aiming for sub 100 millisecond response for natural feeling movement. Verification involves both lab simulation and user trials. Failures inform design movements, creating a feedback loop between testing and engineering. In essence, reliability testing transforms innovation into something clinicians can trust and patients can depend on daily. The next generation of prosthetic arms will blur the line between biology and technology. Direct brain computer interfaces will bypass muscles entirely, decoding neural activity to control movement. Engineers are already developing sensory feedback systems that allow user to feel pressure, texture, and temperature through artificial touch. Miniaturization will make electronics lighter and more power efficient, while machine learning will enable adaptive, self-calibrating systems. On the infrastructure side, open source signal frameworks will accelerate research and standardization across the field. As healthcare systems like the NHS expand access, the focus shifts from novelty to normalization, making intelligent prosthetics available to anyone who needs them. The future isn't just about movement, it's about restoring sensation, agency, and confidence through engineering.